So, you are welcome to today's lecture on the sampling distribution of sample proportion. Here is the plan for our discussion today. We will start with an introduction and we will highlight what the sampling distribution of a sample proportion is and why it's important. We will discuss key concepts like the mean, variability, and shape of the sampling distribution. Then we will explore the normal approximation, its conditions and applications, including Z-scores. We will walk through practical examples and real-world scenarios to deepen our understanding. Finally, we will conclude with applications, exercises, and make comparison between binomial and normal approximations. By the end of the lecture, you will be able to achieve the following. One, you understand the sampling distribution of a sample proportion, including its definition and factors affecting variability. Two, you will be able to apply the normal approximation for large samples using conditions and set scores. You will be able to analyze and solve problems, including computing the standard error and working through real-world case studies. And finally, you'll be able to we will explore practical applications such as constructing confidence intervals and performing hypothesis tests. So these objectives will help you connect the theoretical concepts to practical applications. So let's kick the ball rolling. By definition, the sampling distribution of a sample proportion describes how proportions vary across all possible samples of a fixed size. In essence, if you just a minute to be able to put down some notes. Let me. I want to be able to do some writings. Um, so let's. I'm coming. I want to make some writings. Where do I go? Just a minute. Uh, okay. So here, if you have a population defined as P, your population is this. From this sample, a fixed sample of size small n can be taken. And then you can have small samples of that size, as many samples as possible of size n drawn from this population. And from each sample, you can obtain the sample proportion, small p. So from sample 1, you can have the first proportion. From sample 2, you can have another proportion. And so you will have as many proportions or as many sample proportions as the samples that you have drawn. So sampling distribution of the sample proportion simply describes how the sample proportions from all possible samples, how they vary across from one sample to the other. I will repeat the explanation. You have a population, and from this population, you draw all possible samples. Sample 1, sample 2, sample 3, sample 4. And from each sample, you obtain sample proportion. So from sample 1, you obtain P1 as the sample proportion from sample 1. From sample 2, you obtain sample proportion from sample 2. So you will have sample proportion for all possible samples that you have drawn from the population. So sampling distribution of the sample proportion simply describes how the proportion you have, or the sample proportions, how they vary across the possible samples. So that is the definition of sampling distribution of a sample proportion. So it simply represents the the distribution of sample proportions from all possible samples drawn. And the most important thing is that the sample must be fixed. In other words, for the first sample, you have a fixed size. Maybe n, small n is equals to 5. Then the sample 2 must also have a fixed, the same size, 5. Sample 3 must also have the same size. So we consider all possible samples of a given size, of a fixed size. So why are we doing all of this? Why is this very important? One, it helps us to really estimate the population proportion. The population proportion sometimes is unknown. So by taking all possible samples and then analyzing the distribution of the sample proportions from all possible samples, we have idea about what the population proportion will be. And we'll be able to construct confidence intervals. It's also very important for hypothesis testing. In other words, the knowledge of sampling distribution of a sample proportion is critical, is very important if we have to test hypothesis about the population proportion. So that helps us to determine if our sample result is statistically significant or not. We will still get to know more about those terminologies. So we have an example here. For instance, if a survey reveals that 60% of people exercise regularly in a sample of 100 individuals. Sorry, the survey is about whether people exercise regularly or not. Let's even say this population is about a city. It may be very difficult to know exactly the proportion of people that exercise regularly. That proportion of that proportion will have been the population proportion. but because it's difficult, so we need to estimate. So it's unknown, so we need to estimate. So a random sample of 100 individuals were sampled or were surveyed, and we assume that, let's say, when they were interviewed, do you exercise regularly or not? So 60% of the people claim they exercise regularly. That is coming from the sample of 100. Of course, we don't know yet what the population size is, but from the sample of 100 that we have taken, we 60% claim yes, that they exercise regularly. From here, we want to know how this result will vary across repeated samples. In other words, if we take another set of 100 individuals who that may likely be different from the first 100, then we have another sample. If we take another, we have another sample. So the question is, how does this proportion vary across sample? Am I going to get the same proportion in another sample? So those are the kind of question we would love to address. The understanding helps us to have a very solid basis for statistical inference. So here you have the sample, the formula for sample proportion. So if you want to compute sample proportion, is denoted by P, the small p here, and then X is the number of successes, and then N is the sample size. So in that previous example, for instance, out of 100, 60 claim to exercise regularly. But here again, we have another example. Very simple example to illustrate how to calculate sample proportion. So in a survey of 200 voters, if, for instance, 142 support candidate A, then we can talk about the proportion of the voters that support candidate A. And that proportion will be the number of voters that support candidate A over the sample size. So here, the sample size is 200, and the number of voters that support candidate A constitute the number of successes in this example. So by definition of proportion, it is number of successes, that is, number of voters who support candidate A over the sample size. So in this case, the proportion is 0.1. And in terms of percentage, that is 71%. So this is an estimate of the population proportion. This is not the population proportion. It's just the estimate which is obtained from the sample. So how reliable is this estimate? That is the big question, because that is why the sampling distribution comes in. So sampling distribution helps us to make sense from that estimate. Now, you have several sample proportions, P1, you have P1, P2, P3, and maybe you have up to PK. In other words, these are all possible, these are sample proportions from all possible samples of a given size. So P1, for instance, is the sample proportion from sample 1. P2 is the sample proportion from sample 2. P3 is the sample proportion from sample 3, and so on up to the last sample, K. So Pk is the sample proportion from sample K. We now want to talk about the average of all these sample proportions. Or put differently, the mean of these sample proportions. This collection of sample proportions is what we call the sampling distribution of sample proportions. I repeat, this collection of sample proportions from all possible samples of a given size is what we call the sampling distribution of a sample proportion. So right now, our interest is to look at all these sample proportions. If we find the average, that is, we add them and divide by the number, in this case K. Theoretically, it is going to give us the population proportion. So the mean of the sampling distribution of sample proportions equals to the population proportion, which represents the center of the distribution. And that is the result here. So the mu P there is talking about the mean. This one is talking about the mean of sampling distribution of sample proportions, and that this mean of sampling distribution of sample proportion actually is equal to the population proportion. So that result is fundamental because it describes the location, the center of the sampling distribution of the sample proportions. Just as we are able to find the mean, we can also decide to look at the variance, the standard deviations of this collection of sample proportions. So, of course, you know that the square root of the variance is the standard deviation. But in this case, the standard deviation is the standard deviation of the sampling distribution of a statistic. The statistic here is proportion, so we won't call it standard deviation. Anytime we look at the standard deviation of sampling distribution of a statistic, it becomes standard error. So the standard error is this measure. And for proportion, this is the formula. You will recall that P is the proportion of success and 1 minus P is the complement. So that is the proportion of failure. So that expression, square root of P into 1 minus P, which is the product of the proportion of success and failure, divided by the sample size. This gives you the standard error of sample proportion or sampling distribution of a sample proportion. So this measure, standard error of this measure, that is the standard error of sampling distribution of a sample proportion, is a measure of the spread, how these sample proportions, how they vary, how they spread around the center. That helps us to know how reliable our estimate of the population proportion, how reliable it is. We will talk more about that. So, the implications of this result is that when your sample size is large, as you notice that the denominator there is the sample size. The denominator n is the sample size. So larger sample sizes will reduce variability. In other words, the more sample you take, that makes variability to reduce, and the implication is that you have a better estimate with a reduced variability. So if your sample size is large, then variability is reduced. So the summary of this is that the um, that larger samples provide more precise estimates. That it's always good for you to go for larger sample sizes when you are taking sample. When you are doing your study, you are doing your investigations. So this result is saying larger sample sizes are usually better because it reduces the variability of your estimates. So as we move forward, you will see how this plays out in practical examples. But just get the basic, the fundamentals. So that takes us to, uh, you know, to summarize some of the things we just discussed. So earlier I talked about the center, the spread. The third thing I need to add is the shape. So these three elements are very important uh, concept when it comes to properties of a sampling distribution. So the three key properties: center, that is looking at the average of the sample proportions obtained from all possible samples, and the and that is called the mean of sampling distribution of sample proportions. And we have shown that this is equals to population proportion. Though in practice, it's difficult for you to take all possible samples. You know, it's difficult. So, I mean, just look at even those of us uh, participating in this lecture right now. Uh, if I take sample, if I'm interested in those who prefer coffee or tea, and I take a sample from this class, um, and I get my from the first sample, I can get a proportion, call it P1. If I take another sample, no, uh, but how practicable is it for me to take all possible samples, let's even say of size 10 from this class? It might be extremely difficult. So in practice, uh, you won't be able to get all possible samples. Also, the population may be finite, may be infinite, or may be quite large. That's where these theoretical results become very helpful. So we can we know that the mean of the center is always equals to the population proportion. You know, the center of the sampling distribution of the sample proportions is always equals to the population proportion. So we can invoke uh, that result. In terms of the spread, which I said is concerned about the variability, how the proportions, how they vary across several samples. Uh, we have shown that. You have seen the formula, which is the square root of the product of the proportion of success and failure divided by uh, sample size. But we are also more interested in another property, which is the shape. The shape uh, is very important. Uh, and in the previous lecture, I talk about one shape that is of interest to us in statistics. That is a normal shape. In other words, if I look at the piece P1, P1, P2, P3 to PK, what shape will it give? I know, will it have a normal shape? Will it have a normal shape or not? So if we plot the histogram of the sample proportions, will it have a shape like a normal one? So uh, here we notice that the distribution of the sample proportion approaches normality only when the sample size is large and able to satisfy two conditions. No, one is that the product of the sample size and the proportion of success must be greater or equals to 5. And the product of the sample size and the proportion of failure, this is the proportion of failure, must be greater or equals to 5. So before you can, before uh, the the distribution can, have a shape or a normal shape, you know, the sample size must be large and ensure that the product of the sample size and the proportion of success is greater or equals to 5, as well as the product of the sample size and the proportion of success is also greater or equals to 5. Those conditions must be met. So we need to understand these properties, to be able to interpret our results, more accurately. So let's uh, consider a scenario here, a scenario in which a survey is conducted and 40% of adults um, exercise regularly. They claim they exercise regularly, uh, and the sample size uh, is small n, which is equals to 100. So here we can compute the standard error using the expression there. So standard error is the proportion of success. So from that population proportion, that's what we know about the population proportion anyway. No, so so the 40% uh, indicates that in the population 40 uh, 40 out of 100 exercise regularly. So the standard error gives 0.049. How do we interpret this? This is simply saying that the variability in sample proportions across repeated samples is 0.049. That is, the variability of the sample proportions of all sample proportion from all possible samples, the variability is 0.049, and that the variability or the sampling distribution we center around 0.4. So which means, let's say you have your stuff like this. So this is the center, this is 0.4. That's the center. So the variability measures the spread. This is so it measures the spread around this 0.4. So the smaller the measure of the spread, as earlier mentioned, the more reliable the estimate of the population proportion that you have. So let's now look at sampling distribution of difference of proportions. This is situation where you have maybe two different populations. Maybe this is population 1. So population 1, pop 1, and you have another population, maybe pop 2. This is not this. Pop 1 is not is not is not is a population, maybe a population that is different from population 2. For instance, population 1 could be population of students that took this course last session. And then population 2 could be the population of students currently enrolled for this course. So you have two different populations. So sometimes we are interested in comparing proportions from these two groups. We might be interested in proportion of students who fail the course. So maybe they are not going to be the same. So we might be interested in whether the proportions are the same or not, or we are interested in the difference between the two, the proportion of failure in the two populations. So that to understand the difference, we can also employ sampling distribution of the difference between sample proportions. And that is given by this expression. So if you have, so if you take a sample from this population and you take another sample from this population, so we can use the difference of the two sample proportions to estimate the difference of the two population proportions. So sampling distribution of difference of sample proportions is simply P1 minus P2 in this case, which is the difference between sample proportion from population 1 and the sample proportion from population 2. So the difference represents the mean. This value represents the mean of the sampling distribution of the difference of two sample proportions. So I repeat, this represents the mean of, that's why you can see in the property, the mean, this one represents the mean of the sampling distribution of the difference of two sample proportions. So, and this simply means this distribution of the difference, this mean of the sampling distribution of the difference of two population proportion, two sample this mean of the sampling distribution of the difference of difference of the difference of all possible samples of a given size is equals to the difference of the population proportions. So, in other words, if I take P1 here, for instance, I take a sample from population 1, I take a sample from population 2, I find the difference. So I take another sample and from population 1, I take another sample from population 2, I find the difference, and I look at all the differences from all possible samples that I've drawn. That gives me the sampling distribution of the sample of the difference of sample proportions. So the mean of this sampling distribution is nothing but the difference of the population proportions, the difference between the two population proportions. So that's what this is saying in terms of the first property. So the center of this difference is actually the difference between the two population proportions. And so this is the measure of the variability. So P1 there is referring to the proportion of success in the population 1, and 1 minus P1 is the proportion of failure in population 1, and N1 is the sample size taken from the population 1, and P2 also is the proportion from population 2, the proportion of success from population 2, and 1 minus P2 is the proportion of failure from population 2. And N2, small n2 there, represent the size, the sample size from population 2. So the standard error gives us how this sample, the difference of two sample proportions, how they vary around the center. So we have a scenario there where you have in a city, in maybe city A, you have 60% of the residents exercise. That is the proportion of the population of city A that exercise. The sample size is 100. Then the second city, we have the proportion of the resident that exercise to be 0.7, and the sample size is 120. So we have two populations. Here, city A is one population, city B is another population. And so we might be interested in, okay, this is not even about exercise, sorry, it's about vaccination rate, maybe COVID vaccination or so this is about vaccination rate. Sorry for that mix up. So in city A, you have uh, you have 60% vaccinated, and in city B you have 70% vaccinated. So the standard error there, which is approximately, or well, is equals to 0.065. That tells us that the standard error of the difference is 0.065. So the variability, that is the variability in the difference of proportions. So that's the measure of the variability in difference of proportions in the two cities. Um, what that simply tells us is the extent to which the difference of proportion vary from one sample, to another. Uh, of course, this helps us quantify the variability in comparing these two proportions. Now, we have a practical exercise there, which you can lay your hands on. So here you have to simulate a sampling distribution of sample proportion. The objective is for you to just do some computational task. So you want to simulate sampling distribution of a sample proportion. So the step one is you generate a population with a known uh, proportion of success to be 0.5. You draw a random sample of 100 of you know and so you draw from that population, you draw 1,000 samples. You draw 1,000 samples. So and then you compute the proportion of success for each sample, and then you plot the sampling distribution. We are still going to see example of that later in this course. Now let's talk about the normal approximation for large samples. We mentioned this earlier, and I said when you have large samples, the sampling distribution of the sample proportion becomes approximately normal, even if the population distribution is not normal. So this allows the use of normal probability method to be able to calculate probabilities and also construct a confidence interval. I've also talked about the conditions for normal approximation. The sample size must be large, and the the product of the sample size and the proportion uh, must be greater or equals to 5. Same thing for the product of the sample size, and the proportion of failure must be greater or equals to 5. Uh, this result actually uh, simplifies statistical computations uh, by allowing the use of Z scores, that is the standard normal scores, to calculate probabilities and to also construct confidence intervals. So the approximation is very useful when you have large scale studies and in most practical project, or research work. So um, let's look at yes, how do we now compute the how do we compute the uh, standardized scores with normal approximation. So that's what you the expression for the standardized score is what you see here. That is Z equals to the sample proportion minus, that's the sample proportion minus the population proportion divided by the, the standard error of the sample proportion. So remember, small p is the sample proportion, and the upper, case p, the capital P is the population proportion, and then the SC subscript P is the standard error of the sample proportion. That is the formula you use to compute the Z score. This is the Z score formula, and the formula allows us to standardize the sampling distribution of the sample proportion, and it makes it much easier to calculate probabilities. So it, we can easily convert the sample proportion P to a standardized score relative to the distribution, the sampling distribution. So if we calculate the standardized score as Z, then we can easily calculate probabilities. So since it's assumed to be normal, so this is the this is the this is the center, so which is your P, and then of course we can calculate any interval, let's say A, B, no, A, B, sorry, So we can calculate the probability that a proportion will lie between A and B or no. So we can also use this to perform hypothesis testing and determine significance level. So in other words, probability calculations can help us to determine how likely a sample proportion is given the population proportion. And then the confidence interval can also, using the Z-score, can be used to estimate the range within which the population proportion is likely to fall. We will see how this, this works with an example later. So let's look at this very example. So here you have the let's revisit the polling data example. So the population proportion equals to 0.4 represent the percentage of, 40%, which is uh, this is 40%, which represent the percentage of voters that support a candidate. And the sample size, n is equals to 200. And the observed sample proportion, after drawing the sample of 200, we observe that 45, that's what this is saying, that from from 200, you know, 45% actually support the candidate, and 65% did not support. But this is the population proportion. So this is the observed sample proportion. So we can compute the standard error from this using the expression that you have there. So the population proportion, where you have the proportion of success here, this is 0.4. The proportion of failure is 0.6. And then the sample size taken is 200. And then you do the arithmetic and you get 0. So this is the standard error here. So we can compute the Z-score, which is the sample proportion. Here, this is the sample proportion, 0.45 minus the population proportion, 0.4, divided by the standard error. That gives you 1.45. So in terms of interpretation, that simply says that the sample proportion P equals to, says that this sample proportion is 1.45 standard deviation above the population proportion, which means, of course, this is the normal shape, and then this is the population proportion P. So it means this P equals to 0.45 is 1.45 standard deviation, above on this side. Sorry, on this side. So, oh, uh, so is one is above 1.45 standard deviation above the population proportion. So this this set score helps us to determine whether this result is statistically significant or not. We will still talk about concept of significance or not significant. That will come up in a subsequent lecture. So you can look forward to that. But at the moment, our interest is how to compute the Z score and how to interpret the Z score. So here, the Z score for for P equals to 0.5, you know, the standardized value is 1.45. This is the actual proportion, but this is the standardized value. So interpreting it is simply saying that this proportion is this value standard deviations away from the population proportion. So that is that. Um, Now, uh, to really make the discussion a bit more lively, let's uh, look at we can visualize. I've tried to do that. We can visualize the binomial distribution and its normal approximation for the sample proportion. So in visualizing, uh, the key features, features are what to see above. The first one, uh, remember that the binomial distribution is discrete. So you have the 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 bars representing the the size of the individual in, element, and then the normal approximation uh, we can be superimposed on the smooth curve. Um, so we can also visualize by seeing how sample size increases as the binomial distribution gets closer to the normal approximation. I will show you the oh, uh, I will show you those things very shortly. Um, so when should we avoid normal approximation? Uh, I've told you we can only invoke normal approximation if NP is greater or equals to 5 and N1 minus P is greater or equals to 5. Therefore, uh, we won't be able to invoke normal approximations if the sample size is very small, and that will either make the product NP to be less than 5 or make N1 minus P to be less than 5. If any of these situations arises, then the normal approximation will not be reliable. In other words, the shape will not approximate to a normal shape. So this can happen in two extreme situations. One is when P, that is the proportion of success, is close to zero, very small, or when the proportion of success is close to one. So when it is close to zero, you know it's like the number of successes is very, very small. And when it's close to one, it's like the number of successes in the sample is almost the same as the sample size. So the sampling distribution will be skewed and not normal. So you might have a skewed distribution. A skewed distribution has a longer tail, either to the left or to the right, as the case may be. So the distribution is skewed when when you have extreme proportions, very few number of successes, or nearly all samples are, are successes. So when this happens, we will not be able to use the normal approximation. The z-score that we use will not be appropriate. And so for smaller samples, the binomial distribution remains the only option. So, but we won't go into that. Just know that for small sample sizes, when the product of the sample size and the proportion of success is very small, less than 5, then you cannot use the normal approximation. So rather you use the binomial, which is what which is the exact method, that way. So again, you have a practical exercise here to do, but this with respect to binomial, to normal approximation. So you want to compare the binomial distribution and the normal distribution. So in this, you can write out code to do the simulation. I will share this code with you, and in the practical class, you'll be able to run it on your R. So the first step will be to generate a population proportion, of P equals to 0.6. Then you take samples, this time multiple samples, n equals to 50, n equals to 100, n equals to 500. Then you plot the binomial distribution, and then overlay the normal approximation. So you have something like this. So look at the this is a simulation uh, that you know that I did, which you can also reproduce. If you are able to write your own R script, you have something like this. But um, let's look at this to be able to bring home the point we are trying to emphasize. Um, you look at the the plots. There are three plots, on the screen. So they represent the plot of binomial versus the normal approximation, and you have um, uh, for different sample sizes. The first one, this is for sample size n equals to 50. You can see the shape. Then for n equals to 100, you can see the shape. For n equals to 500, you can see the shape. But one thing you will quickly notice is that when equals to 50, the binomial distribution, which is the one in blue, is more discrete. Uh, is more discrete, which means you can see uh, uh, the lines, the blue lines breaking. Uh, as you go to 100, you see the lines, those still breaking but very close together. But at n equals to 500, you can see the lines, the blue aligns closely with the normal curve. That's one thing. So it shows that um, uh, as the sample size increases, then uh, the even the binomial approximate to a normal distribution. So that is the point we are making. And the x-axis represent the number of successes. Uh, in the first plot, this represent the center, and you can see the spread around the center. So out of 50 um, out of 50 samples drawn, uh, 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 the proportion of success, is the number of successes is 30. Out of 100, the number of successes is 60, and out of 500, the average success is 300. So you can see how the uh, how the the number of successes in the samples, how they spread around the center. So let's now summarize the key points from our lecture today. Of course, everything I said there, they are also discussed here. So I won't waste time to go through that. Everything I've explained. So they are all discussed here, and I will share this with you. So, what are the key takeaways from this lecture? The first thing is that the sampling distribution of sample proportion describes how proportions vary across samples. How sample proportion will vary from one sample to the other sample. That's one major thing, that if you have a population, you take a sample, and from this sample, you obtain the sample proportion, which is the proportion of sources in that sample. And you go back to the population, you take another sample of the same size, and you obtain the sample proportion for the second sample. The proportion, will vary again. And as you take different samples and obtain different, as you take different samples and obtain the sample proportions will vary from sample to sample. That's one major result, one major thing that we have established. Two, we have also established that larger sample sizes lead to smaller standard errors, which means if you want to improve precision of your estimate or estimate of the population proportion, you always need to take large samples. And then we've talked about uh, the fact that the concept this concept of the center, of the spread, and of the shape, they are very, very crucial to constructing confidence intervals and testing hypotheses, which will come in our subsequent lectures. Then we've also talk about the normal approximation, when it is valid and when it is not valid. It's valid when the sample size is large, and when the product of the sample size and the proportion of sources is greater or equals to 5, and the product of the sample size and the proportion of failure is greater or equals to 5. But if otherwise, then you cannot invoke the normal approximation. You have to use the exact binomial, we which we we also look at the simulation to compare the binomial versus the normal approximation, and show that yes, as the sample size increases, we can see how the binomial approximate to normal. So that is the summary of our discussion. We will now, as usual, go to the multiple choice questions for you to for purpose of uh, evaluating your learning, in this lecture. So let's start. Um, this time you have to give us your options. I hope, yes, give us your options. By the way, are there questions that I need to respond? I cannot see any question, but let's continue. Write your write your okay. The first question is, what is the primary condition for applying the normal approximation to the sampling distribution of the sample proportion? Maybe this is one thing said, in my concluding when I was about to round up that lecture. So, what are your options? Are you responding? I cannot see anybody yet responding. So write the number, the question number, and also write the question number. This is question one. Write um, your option A, B, C, D. A, B, C, D. Only one. Okay, let me. Yeah. I need to. Okay. Yeah, so I can see some are already responding. B, 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 B. Is that a consensus? Is that a consensus? I can see many people choosing B. Saminat, Teslimot, Oladipupo. That's great. Um, Sorry, I can see this. Let me just stop sharing a bit and change. Uh, Let me show a window. Maybe this will be better. Okay, there seems to be a consensus as far as this question one is concerned. So you are correct. This is the so I can see the consensus around B. That's a good one. That's a good one. Just a minute. So let's move to the. So this is the correct answer for that. Let's move to question two. What is the formula for the standard error of the sampled proportion? What is the formula for the standard error? That's the formula for measuring the variability of the sample proportions. So this is question two. What is the formula for measuring the variability of the sample proportion? Again, it appears consensus is around B. That's a good one. That's a good one. So some people are not active. They are not responding. I can see great people here. So let's go to the answer is B. You are correct if you have chosen B. The next question is what does the standard error of the sample proportion, what does it represent? That's question 3 now. Question 3. What does the standard error of the sample proportion represent? What does the standard error of the sample proportion represent? The variability of individual data points, the spread of the sampling distribution of the sample proportion, the range of the population proportion, the mean of the population proportion. Again, uh, I can see people struggling between A and B. People struggling between A and B. I can see player one choosing A, Malik choosing A. Actually, the variability of individual data point is measured by standard deviation, not standard error. Not standard error. So Ifedayo, player one, Malik, uh, that is that option is not correct. So you can change your option. So the correct answer is B. Now question 4. Question 4. Question 4. Remember to write question 4 and your option. When using the normal approximation, what shape does the sampling distribution of the sample proportion take? What shape? When using this normal approximation, what shape does the sampling distribution of the sample proportion take? Yes, there is a consensus here. Everybody is talking about B, B, B. Okay, that's fine. That's fine. So the correct answer is B. Let's go to this. You do a little bit of calculation here. Do a little bit of calculations here. If P, that's the population proportion, is 0.4 and the sample size of 200 is drawn, then what is the standard error of the sample proportion? What is the standard error of the sample proportion? If P, that is the population proportion, is equals to 0.4 and sample size is 200. So what is the standard error of the sample proportion? Yeah, you know the formula. You can quickly do the calculation, right? So let's see those who are able to do it. So there seem to be consensus around C. There seem to be consensus around C. Yes, let's look at the answer. So this is the formula you will use, which is standard error of sample proportion equals to the square root of the proportion of success times the proportion of failure over the sample size. So you substitute accordingly and you get your answer. So the correct answer is C. Let's go to question 6. Question 6 says, why does normal approximation become more why does the normal approximation become more accurate with larger samples? Yes. You if you follow the discussion around the simulation, you'll be able to answer this one correctly. Why does the normal approximation become more accurate with larger samples? So A, the standard error increases with larger samples. B, larger samples make the population more uniform. C, the sampling distribution of the sample proportion becomes approximately normal as n increases. D, the population proportion. There are consensus around B, but I don't think uh, people, I don't think you really, maybe most people seem not to understand the. Okay, so what is the solution here? The correct answer is C. Don't be sad. Correct answer is C. For most of you, just the correct answer is C. And what is C? C is saying the sampling distribution of the sample proportion becomes approximately normal as n increases. It is the sample, the size of the sample that guarantees the normal approximation. Don't forget. Question 7. Question 7. What is the Z-score formula for sampling distribution of a sample proportion? What is the Z-score formula? What is the Z-score formula? Samiat, that's too fast, too good. Uh, uh, Player one, Michael, that's also good. I think everybody should go. Who is this? Olade Pupos. Similoluwa, you need to check again. Njoku, you need to check again. I think you guys, yes, consensus are now around B, which looks great. So, what's the correct answer? The correct answer is B, which is small p over capital P, that is sample proportion minus the population proportion divided by the standard error. That's the formula for the standard score. And I've told you that formula helps to convert the proportion to standardize the value. So let's go to the question 8. In a pool, you need to do some calculations here. Question 8. In a pool, 70 out of 100 people said they prefer a product. So in that case, you have the sample proportion to be 0.7, and then you are given that the population proportion is 0.65, and the sample size is 100. So what is the Z-score? Just apply the formula, the previous formula. Nobody has responded. It shouldn't be a difficult calculation. We've just used the formula. We just discussed the formula. People are still pressing their calculators or phone. Yeah, nobody has responded to question 8. I'm waiting for the okay. Player one has broken the silence. As Saminat, Master, Teslimot. Yeah, so uh, uh, oh, Olamide, no calculator. Too bad. Too bad. Try to borrow calculator next time. This is a statistics class. So who else? I can see a lot of other people, Ifedayo, Oladipupo, Joshua. That's great. So let's look at the answer to that. So this is the way to calculate. First of all, you have to calculate the standard error, which is 0.047, and then you compute the Z score, which is this, the small p, sample proportion 0.7, the population proportion 0.65, divided by the standard error, which is, so you solve this, that gives you 1.3. So the correct answer is C. Correct answer is C. Unfortunately, most people got it wrong. People are now deleting and replacing. Well, don't worry. You learn. No, when you make mistake. Okay, let's go to uh, question 9. We are almost rounding up the lecture. What happens if NP is less than 5 or n into 1 minus p is less than 5? What happens? The normal approximation is invalid, the standard error becomes negative, the sampling distribution is always normal, the population proportion increases. What's your answer? We've talked about this severally. The normal approximation A is invalid, the standard error becomes negative. Okay, Malik, Tobilola, Joshua, Semina, Player, Teslimot, Odumbaku, and so on, Wuraola, seem to go for A. Well, that's good. That's good. That's good. So, what's the correct answer? A is correct. So you can clap for yourself. That's a good effort. Finally, what alternative method should be used if normal approximation is not valid for small samples? Question 10. What alternative method should be used if the normal approximation is not valid? In other words, if those two conditions, NP is less than 5 n if n 1 minus p, n into 1 minus p is now, what should we do? Use the exact option binomial approximation. C says artificially. D says skip statistical inference. Don't skip statistical inference. See, the answer has been a lovely discussion today. The correct answer is B. So that is the end of our lecture today. Thank you very much. Uh, we continue our discussion on the WhatsApp group. Uh, Send your questions and comments. Feel free to uh, also encourage your colleagues to subscribe to this channel and take care of yourself. We will meet again next week. Until then, take care. Enjoy the rest of your day.